All right, so welcome to our next lecture on algebraic topology. This is officially lecture 1. The last lecture was an introductory lecture. I'm Norman Wildberger. Okay, so what we want to do now in the next few weeks is to introduce some basic objects which we're going to study. Okay. Every mathematical subject is centered around some examples, some objects that we're studying. And the richer and more interesting the examples, the richer and more interesting the mathematical theory. So we need some examples to begin our study, and that's what we're going to do at first. So we're just going to talk in a kind of an introductory way about a number of different objects. And we're going to start off with the simplest kind of things, one-dimensional objects. Okay? So we're going to talk a lot in terms of pictures and a little bit informally. Okay, so what are some examples of one-dimensional objects? Well, there's a line. Okay, a line in the sense of Euclid. Euclid, when he said a line, he meant a straight line, and he meant that the line keeps going in that direction, and it keeps going in that direction, meaning that you could always extend it. Okay, you could always extend it in either direction. That's a one-dimensional line. And for us, we'll think of this as sometimes called an affine line. And we'll give it a name, A1. I'm not going to call it R1. In other courses, you would say this is the real number line. But I don't really believe in the real numbers. I believe that the rational numbers are the fundamental building block of mathematics, and that you've all been deluded, and I've been deluded too, for many decades, in thinking that the real numbers are the fundamental building block. So in any case, we'll leave that issue for later. We'll talk about that. But right now, you can think of it as just a line, real line if you really want, rational line if you are thinking a little higher plane. Okay, then we'll call that the affine line. We'll write A1 so that we don't have to decide what exactly it is. Now we're talking about topology, and so this is really homeomorphic to a squiggly line. We can bend it, we can deform it. As long as it sort of keeps going in both directions, then it's really the same for us in this course. In geometry, it's completely different, but for us, it's the same. So continuous deformations are allowed. This is just a continuous deformation. All right, so that's obviously one important one-dimensional object. And there's another important one-dimensional object, of course, which is a circle. And we'll give that a name. We'll call that S1. And that's also deformable. And if we deform it, we could get something like that. As far as topology goes, those are the same objects. They're the circle. Okay, so let's have a look at this circle. The circle appears in mathematics in a lot of different ways. And we're going to have to be prepared to look at the circle in a lot of different ways. So the first way, I suppose, the one that you're mostly familiar with, is in terms of the usual Euclidean plane with some kind of markings, perhaps an X and a Y. And then the circle, say, might be chosen to be the unit circle. And that's given with equation x squared plus y squared equals 1. That actually belongs then to a very simple example of something in algebraic geometry. It's an example of a variety. It's given by a polynomial equation. It's a zero set of a polynomial equation. Another way of thinking about the circle is as a curve. Okay, so we can think of it in the same way, but we can think of it as being given by the motion of a particle. And the standard way of doing that is to introduce an angle theta and say phi of theta is cosine theta sine theta. And then we have to prescribe what's happening to theta. Theta is going between 0 and 2 pi. That's the usual transcendental parameterization. I call it transcendental because the two functions, cosine and sine, are actually given by infinite power series. There's an alternate parameterization of the circle, which is a rational parameterization, and I'll write it as E of h. And I'll define that to be 1 minus h squared over 1 plus h squared, and 2h over 1 plus h squared. That's called rational parameterization. And it's very important because it provides an algebraic alternative to this transcendental parameterization. These are what are known as rational functions. They're just polynomials divided by polynomials. And what is the range of values for h? Well, h is any number in whatever number system we're working with, or also sort of a special value, infinity, with quotes. What is E of infinity? Well, we could define that to be, if you know some calculus and you put a very big number in here for h, then that first entry is going to be minus 1, and that second entry is going to be 0. So it's reasonable that E of h be defined to be the point minus 1, 0. That way we get every point corresponding to a parameter. Now, in one of my videos in the wild trig series, I talk about parameterization of a circle, and I derive this. But let me just remind you how this parameterization goes. So there's 1, there's minus 1. The idea is pretty simple, sort of ordinate x and y. If we choose some point on here with coordinate h, and we join that point to the point minus 1, 0, and see where the other point of intersection is, then this turns out to be exactly E of h. Okay? So the significance of h is that it's this coordinate, the y coordinate of this point here. So this corresponds to h equals 0. This corresponds to h equals 1. This corresponds to h equals minus 1. And if h was equal to 2 up here, then this would be h equals 2, and so on. This point here is h equals infinity. All right, our third way of looking at a circle is in terms of what's called a moduli space. It's a very simple example of what's called a moduli space, but I won't define what this is, but let's just say informally that this means a space of possibilities. Rather informally, and let me illustrate what I mean. So we're also looking in the plane, and the plane I will write as A2. Okay, that's the plane. You can think of R2 if you like. I prefer to think of the rational plane, where A is actually the rational numbers. But in any case, there's the plane, the usual x, and y axes. And the things that we're interested in here are the one-dimensional subspaces. So we're interested in one-dimensional subspaces. If you think of this as a vector space, two-dimensional vector space, it has one-dimensional subspaces. And the one-dimensional subspaces are just lines through the origin. All the lines through the origin. So one-dimensional subspaces is the same thing as lines through the origin. So once we've defined what a one-dimensional space is, we can ask a very natural question: is what does the space of all lines through the origin look like? What does the space of all lines through the origin look like? And the answer is that it looks like a circle. And let's explain why that is. So how can we identify this with a circle? Well, the idea is to put a circle into the picture, but it's not the unit circle that's over there. It's rather a circle that we could put right here, like this. Okay. So if we look at a circle that goes through the origin, and then we look at these one-dimensional subspaces, well, this one intersects the circle there. This one intersects the circle there. This one intersects the circle maybe somewhere down there. Every one-dimensional subspace intersects the circle in a unique point other than the origin, because they all pass through the origin. But every one-dimensional subspace intersects the circle in an additional point, except for the horizontal line. The horizontal line is special because it's tangent to the circle. It doesn't meet the circle in a separate point. It meets the circle rather at this point doubly in some sense. So this line here, the horizontal line, gets associated in this picture with this point, with the actual origin. And so we see that the space of all lines, or all lines through the origin, is topologically a circle. So the space of all one-dimensional subspaces, which we're going to give a name, we're going to call that P1. We're going to call that the projective line. Okay, so P1 is by definition the space of all lines through the origin, or one-dimensional subspaces. And what we've seen here is that topologically, this is really the same as a circle. This picture shows that what we're calling P1 is essentially the same as a circle topologically. In higher dimensions, which we'll get to, we'll see that the situation is more complicated. Okay, there's other ways of thinking about the circle. So that was our third one, I suppose. So D, we can think of a circle as being a loop of string. Or rope. In perhaps 3 dimensions. In 3-dimensional space, which we're going to call, no surprise, A3. So we don't have to restrict ourselves to the plane. We can think about a loop, a closed loop in 3 dimensions given by a piece of string very concretely. And that allows us to draw pictures of circles in somewhat novel ways. For example, this is going to test my artistic abilities here. Okay, make a little bit of shading here, maybe make that a bit rounder. Shading. Okay, it's sort of a fat string now, but it's now a knot. This is still topologically a circle, but it's now in 3-dimensional space, and this is something called the trefoil knot. Well, that's not the only way we could, of course, make a knot. There's lots of knots, but in particular, there's also this one. Which I'm shading. This is also a knot, but it's sort of the mirror image of the trefoil. If you have a piece of string, you can make these things, and they appear to be different. That is, if you make 2 of them and then you take one of them and try to manipulate it so that it looks like the other one, you have a hard time. You start suspecting that these are essentially different knots. In fact, with a little bit of experimentation, you pretty soon become convinced that they are different knots. But to prove that they are different, to prove that somebody could not come along and very cleverly distort them and twist them and turn them and so on to create go from one to the other, is a highly non-trivial question. So a natural question is, are these 2 knots equivalent? And this is a different notion from homeomorphic. They're both homeomorphic to a circle, but are they equivalent under deformations of the ambient space? Under deformations, say, in our 3-dimensional space. That was an unknown problem for a long time. So that's one of the things that we're going to be making contact with. We're going to be talking about knot theory. This is just an introduction to some ideas. I'm just giving you simple examples. We're going to talk a little bit about knot theory in this course. And so we'll have to then be a little bit more clear about what this notion of equivalency is. But just another manifestation of a circle. Okay, here's another one. A polygonal representation. Our circle, S1, can be deformed to give a triangle, which can also be deformed to be a pentagon or any other polygon you like. Topologically, these are all the same. And when I do this, I should just make sure that we know that we're only talking about the actual one-dimensional curve itself, not the interior. It's empty interior. Okay? When I'm talking about this triangle, I'm just talking about this rigid frame, as in a face of this. Okay, here's another way of thinking about a circle. It's in terms of identifying intervals. Okay, what do I mean by that is I'm going to create a circle for a one-dimensional creature. Imagine that we had a one-dimensional creature that only lived on a line. Not just a two-dimensional creature, but a one-dimensional creature. And we wanted to try to explain to this creature what a circle is. How could we do that? Well, what we could do is we could take an interval, a closed interval, unless I say otherwise, and we'll call its endpoints A and B. And then we could take another interval, and we could call its endpoints B and A. And now what we could do is we could identify the two B's, and we can identify the two A's. And what do I mean by that? Well, it means that, so for example, if the little creature, okay, let's make it a little worm. Okay, there's the little worm. All right. The little worm is let's say it's walking along this first interval here, and it gets to B. Well, what we do is we temporarily induce a coma, and we move it, and once it's just about there, it's just about to fall off the edge, but just before it does, we just induce a coma momentarily and move it over to the second one, so that without any discontinuity as far as it's concerned, it's now over there, and it just keeps wandering merrily on its way. It hasn't noticed that that we've lifted it up and put it somewhere else. And then when it gets to A over here, then we lift it up quickly and put it back over here. So as far as it's concerned, it's just going in the same direction as it usually does. Usually, by experience, it knows that if it wants to go back to where it came from, it has to turn around and go back. Okay? But now we're subjecting it to a wildly different experience. It's moving along, and all of a sudden it's back to where it started. Could be very disorienting. It's really gone around a circle. I mean, from our point of view, what we've really done is we've kind of taken one thing like this and another thing like this, and we've glued them together effectively. But the point is that we can mimic a circle in a purely linear way.
Is there any reason why we need the second interval? Why couldn't we just identify? Very
good question. So right. We have some freedom in doing this. We could be a little bit more efficient. More efficiently, we could say, well, why don't we just take one interval and identify that point with that point. Once it gets to that edge, we just move it back to the beginning. And that would, in fact, also be an alternative. And we're going to see sort of both of these kind of approaches when we go up to 2 dimensions. In some sense, maybe this is a little bit more aesthetically pleasing in the sense that there's no, each piece is sort of not identified with itself. This is more aesthetically pleasing in that it's simpler or more compact. Okay, that was number F. All right, we have still another way. Another way of getting a circle is to use a translation on a line. So what we do is we start with a line, which we're calling A1. That's a line. And let's say we give it some coordinates, 0, 1, 2, -1, -2. We can extend in either direction. And now we're going to consider a translation of this line. Let's call it tau. And the translation will just be, so tau is translation by 1 to the right. That's a motion of the this line, and the inverse will of course be translation by 1 to the left. And now what we can do is we can write that the circle is what we get when we take this line and we mod out by this translation and its inverse. Okay, so this is a kind of a group theory concept, but let's just introduce it informally. What this means is that we are considering, we look at orbits of, well, tau and tau inverse and all its multiples and all iterates, let's say, on A1. It orbits. What does that mean? So we choose a point. Let's say that one right there. If we apply tau to it, well, we get that point there. If we apply tau to that, we get that point there. If we go backwards by applying tau inverse, then we get this point here, and then this point here, and so on. So we get a whole family of points. And let's think of that whole family as somehow connected. So let me draw that by just sort of connecting them. We'll put them all in the same family. Okay. And we'll call that one orbit. That's one orbit. We call that x. We can say that that's the orbit of x under the translation and its inverse. And what this statement is saying is that S1 is the same as the space of all orbits. That's what this means. The space of all orbits. So in other words, we think about what happens if we vary x. So if we move x to, say, y, then we get another orbit, which will look like this. And now if you think of the orbits as the fundamental objects, okay, then what happens when we move the orbits is that as we move over, eventually we get back to where we started with. Because as we move x through y and through z and so on, by the time we get to this point here, the orbit comes back to being the same as it was at x. Because the orbit of this point is the same as the orbit of that point. So all the orbits between here and here are distinct, but when we get to this point, we're back to where we started. So the space of all orbits is a circle. Again, it's a purely linear phenomena. There's nothing round about this at all. We're just looking at the line, which is very flat, together with this translation, and that somehow generates topologically the circle. It's going to be an important notion. All these things are important because when we generalize them, they become richer. All right, so next time we're going to ask the following question. You can think about it. The question is, we've now had these two different basic one-dimensional objects. And the question is, are the line and the circle homeomorphic? Are they the same? Well, obviously, kind of no. But in order for us to answer this, first of all, we need to be more precise about what homeomorphism means. We need to clarify what exactly does this mean. And once we've pinned that down, then we can try to come up with an argument that, that distinguishes between the line and the circle. All right. So next time we're going to prove, or at least indicate, why the line and the circle are actually different. And we're going to start with the notion of homeomorphism. So we'll see you then.